دكتور الديزاين بروجكت ما قلتش شيء عنه.
Okay. طيب I just started the recording. Let me welcome everybody again. Muhammad is asking. Muhammad, let me share first my screen before I forget. Design project, Muhammad. It's clear. The details are all over here. What you need to do, the team up, the groups, the two controllers you're going to use, what is expected to do in every one controller. And we have a due date here already. April 21st, I need a proposal of what you're going to do and who are your team members. And you submit it here. Okay?
تمام دكتور، شكرا لك.
Okay. طيب تمام. طيب, back to what we're going to cover today. Today, I'm going to try to finish or cover assembly instructions and directives, then go to embedded software design. So let's start. Last time we were here, and I make sure to upload the slides before the class meeting. Sometimes, by the way, I do some modifications. طيب, swap and here height. طيب. So last time when we started talking about assembly instructions, we talked about load and store, and these are to load to registers, CPU register, and store what's from memory, and store what's in CPU registers to memory. We looked at them. Then we talked about transfer from a register to a register, CPU register. Exchange values two-way between two CPU registers, sign extent. Then to move data from memory to memory, we use the move instruction. You can move a byte or move a word using any of the addressing modes. But the destination cannot be an immediate here. It has to be an address. The source can be an immediate number. And we start here. So we didn't cover this part. I have recorded a demo on a class demo called Flipped Class Demo 1. It's uploaded to the e-learning class page, and the demo I did is there, where we do solve a formula, where we do add and multiply and all these things. So watch it during the weekend if you want. And if you have any questions, you can ask about it in the following class. So you add. We said this microcontroller is accumulator based. Accumulator based, which means when you do a math or logic operation, one of the operands has to be in an accumulator. In an accumulator. The accumulators هم register A, B, and D. تمام? So you have a register مثلا add A, memory location 1000. So you go to memory location 1000. Okay? You have a number here. Let's say 1. You go add 1 to A and save it in A. Okay? If you add with carry to A, in addition to the contents of memory location you provided, 1000 plus A, you add the carry flag value in the CCR register. How many carry flags we have? Only one. What makes it 1 or 0? The last operation that happened. Either after the operation, the addition, the subtraction, the multiplication, the carry can rise, set, or clear. Okay? Whatever the value, you can add it by adding with carry. Subtract from A. Subtract from A with borrow. يعني with borrow, يعني استقراض يعني you subtract the carry flag. Why do we need to add carry sometimes? يعني when you add 1 plus 2 in decimal 3 صح؟ بس if you have here مثلا let's say 9 plus 2 وهي 19 وهذه 22, so 9 plus 2 is 11, so 1, and the carry here, you cannot ignore this carry, you have to add it to these two numbers. So you cannot, in the second stage, when the second place, 1 plus 2 is 3, it's not 1 3, you have to add this one, which is the carry. Okay, same here, when you add an 8-bit number, 8-bit number, 8-bit plus 8-bit, fine, you can just do add, right? Add A, صح? Is it how we write it? Add A, yes. Here are the instructions. طيب, add, where are they? Add A. Or you can add to B. Or you can add to D. You cannot add to X, an operand. You can add B to X. There is an instruction to add B to X. B to X and store the result in X. You can add B to A. You can add B to Y. Register plus register, okay? But register plus memory location, the only registers that you can add the contents of a memory location to are the accumulator registers A, B, and D. طيب, A, B, and D. الآن, you can add them to an operand, a memory location, and you can add to A and B the carry, okay, with a memory location. You cannot add with D the carry, which means if you are to add 8-bit numbers, 2 8-bit numbers, you can put one of them in memory location and address مثلا 1000 مثلا 12 A مثلا was مثلا let's assume it was 34. You can say add A 1000. This will add the 1 2 plus 3 4. Fine, great. If you want to add 16-bit plus 16-bit, that is also easy. You can put one of them in D, yani, right? The 16-bit, you can say D equals the first 16-bit 1 2 3 4, and the second 16-bit 2 memory location at address 1000 and 1001 01, right? And you add them. You say add D, contents of memory location 1000. You get the two 16-bit registers, and you can add, in this case, the 1201 plus the 1234, right? And no issue. When does the issue happen? If you have more than that, you have a 32-bit number, or 3-byte, or 4-byte, and anything above 16-bit. If you have this number 1 2 3 4 5 6 7 8, هذا operand 1 1 2 3 4 5 6 7 8, and we're talking in decimal, any number above 65k 65,500
36.
65,536.
Yes.
Any number, يعني 70,000 plus 2,000, you cannot perform a 16-bit operation. It's more than 16. You need to split the operation into 2 cycles, or more than one addition. In this case, if you want to add this operand 1 with operand 2 that is already in, well, it cannot fit in one register, صح? it could be in address 2000 here, the operand 1 at address 1000. And here you have, I don't know, whatever number, FF3, yani 16, FFEE 1021, operand 2, FFEE 1021. If you want to add them, this is what happens. You put them like this, FFEE 1021, and the other operand is 1, 2, 3, 4, 5, 6, 7, 8. To add them, you can put this in D and add this up this memory location to it, and say add D. Fine, but this will result in a carry. Okay, so you cannot go add these 16-bit with these 16-bit. You need to add to the carry to it. So you can take these 8-bit with these 8-bit with the carry, and you say add with carry A. Put one of them in A and the other one in B. And the result from here will result in a carry. Okay, you add the carry with these two 8-bits. Okay, we have more details about this. Class demo 1, class demo 1 explains this in detail and actually writes code to add 32-bit numbers. Well, multiply 16 times 16 times 16, you get the 32, then you add it to another 32. So all these details, you can find them in class demo 1. The code is there, and the recording explaining the demo is there. Tamam? But long story short, there are instructions that can add an operand to a register with the carry flag. Same for the subtraction. Example, I had watch, and you can read these examples running on your hardware. Find it in the class demo, and let me know if you have any questions. Instruction execution cycle. طيب. When we speak about an instruction that is in the program memory, instructions are where? In the program memory. The control unit, we talked about this before, the control unit through the program counter fetches an instruction to the CPU, decodes it, and executes it. Okay. Now, an instruction cycle could take one read cycle, one or more read cycle. ليش one or more read cycle? Because the instruction could be a 1 byte or 2 byte, right? And the operand could be 1, 2, or 3 up to 5 bytes, right? We saw this. So you have one or more read cycles to fetch the instruction opcode and addressing information. You have one or more read cycles to fetch the memory operands, which can range from none to 7. Then the CPU will take some cycles to perform the actual operation, the addition. So first you bring the machine code, you bring the opcode from memory, program memory and data memory to the CPU. Then you perform the operation. Then if the result is needed to be stored back in memory, you may take one or more write cycles. So we had read cycles first. Now we have write cycles to write back the results in memory. Okay. If you don't, you don't. So that's optional. Now there is one important thing we need to understand, that a CPU, the CPU can perform only one instruction execution at a time. It cannot be executing 2 instructions at a time. So one instruction at a time, okay, execution. But while it is executing the instruction, it may not be using the memory it may not be accessing the memory, which means the address bus, data bus accessing the memory may be free. Okay, so the control unit at that time, yani CPU, this is the CPU doing execution. Okay, the control unit, okay, may be bringing high memory مثلا memory CPU executing. It's not using this bus that is connecting with the CPU. Okay, so the CPU, the control unit may go fetch some instructions, put it here next to the CPU in something called an instruction queue. Instruction queue. Okay, instruction, where is it? Yeah, instruction queue. Okay, this SCS12 has two-stage 16-bit instruction queue. يعني بمعنى while this is executing, you can go get a 16-bit and a 16-bit opcode, operand for the following instruction, so that when the CPU finishes executing the instruction, it doesn't have to waste time and go fetch, read the memory for the new instruction. Okay, it will find it in a register that is accessible faster for it. Okay, this is a kind of pipelining, and I think you went through it somewhere in your undergrad. طيب, if you see, we're moving faster now because we covered many of these things here and there while. Okay, continuing on assembly programming. First, okay, when we wrote our first assembly class demo, we had something called directives, assembly directives. Like what? Like the مثلا origin 1000. Then we had another directive, define constant byte. We had a label مثلا x1 define constant byte.
word أيضا
1 2. Well, this is a label, and you don't have to use it, by the way. This tells the assembler that when you go generate the code and you send it to the memory, when you program the actual hardware, put this 12, reserve a byte for it at address 1000, start at address 1000, and label. In my code, you can use a label called x1, but everywhere this is used, it's going to be converted to 1000. Yani if I say load accumulator A x1, okay, when you assemble your program or build it, it will convert to load accumulator A with 1000. So you will never see x1 anywhere in your code when after you assemble the program, okay, because this is a label. The origin, go look into in the instruction set. You will not find an instruction set table. I mean, you will not find it there. It's not an instruction. There is no machine code for it. This is a directive for the assembler. No machine code will result from it that you would run on the processor. Okay, we call these directives. Okay. So here we're talking about directives. We're going to look at all kinds of directives, assembly language instructions, and comments. So an instruction would look like this. I don't know. Do I need to show more? Let me open our class demo 1. Let me show you class demo 1, the first class demo we wrote together. If you want, I can open the project here or go to the source directly, right-click, edit, open it in the editor quicker. Okay. So num1 here is a label. Origin, we call it a directive. Define constant word, define constant byte, these are directives. Okay, origin 2000 directive, reserve memory byte directive. طيب. Let's go to the instructions. This instruction. You have the mnemonic, you have the operand, you may have before the instruction a label. The label will be replaced by the assembler with the actual address. يعني هاي branch forever. When we built our program, how did it look like? Let me open the project, the actual real project. I'm gonna open it and run simulation. So if you go look at this instruction, branch forever. Where's the branch? Here in the right window, in the assembly window. Yani we know that our program, we started the first instruction at address origin RAM start, and this was 4,000, yes. So at address 4,000 here, we will have our first instruction, load S here, see, load S. Then you continue. This instruction has a size, and we look. If you forgot these, go back to the recording where we did this demo, and you'll see that load S is a 3-byte instruction that is stored in 4,000, 4001, and 4002. So the next instruction after the load S is the clear. This one is converted to AND condition code register with this number to clear the I bit, and it has a size. So this number here, where my mouse is pointing at, is the program memory address. طيب. We keep moving. So every instruction here in the source will reserve a few memory locations in the program memory, 2, 3, 4, whatever. Okay. The last instruction we wrote here is the branch forever to get into the infinite loop. The branch forever, it happened, and if you give everyone its size, the branch forever is at address 4022. You see that there is no forever. Yani, you don't see a forever. It's a branch. You can, yani this star plus 0 is 4022. You're saying branch to 4022. We don't see a forever. The label is not a machine code. Again, even the origin, this origin, do you see it anywhere here? You don't see it. You don't see it. It's not an instruction, okay? You don't see it. So directives are for the assembler to tell it what to do when you generate the machine code, but they're not here anymore. Okay. Back to what we were talking about. So an instruction, before an instruction, we may have a label, we have the operation field, the opcode, then the operand that the operation will be performed on. Then we may have a semicolon and some comments behind it. And we did this in reality, and there's no point in me go more details here. Directives, and we said that this directive, wherever you write it, this means that any following lines will not be assembled. They will be ignored. Origin tells the assembler that anything I start to use memory after this line, okay, so we say origin 4000. So anything I write here, add, the add will be stored at memory 4000. Okay, the add will be stored here. Yani, it depends on how many locations. Okay, this is the origin. Anything not clear here? Okay. Now the other directives to reserve memory locations in memory. I told you, and I think one of you asked me last time, what is the difference here? These are a group. They all reserve one memory location and indicate what's going to be stored in it. So you can put a label, say array, say whatever, define constant byte or define byte, okay, or form constant byte, then first byte, second byte, third byte, fourth byte. For this one, will go, since we have origin 800, okay, this will book at 800 a byte and store in it 11 hex, then 801 and have 22 hex in it, 802, 33, and 803, 44. طيب, what if I use the define byte? The same, best. Our code warrior, I think I tried this. Sometimes it doesn't accept one of them, but at least one of them works. Okay. Word books words. So this vector table define constant word, it will book a word for the first one, 1, 2, 3, 4 at address. If this was origin 1000 $, this will be 1000, 1001. Then another one, ABC20, and this should be hexadecimal. So, well, what is this minus? A minus? It could be a minus. I don't know. It's a number. Yani, ABC could be. I think it's a hexadecimal. Yeah, and minus 20. Form constant character. This is to, yani, if you want to write a message or something. Form constant character. So if this was origin 2000 at address 2000, you will book a byte for each character, and you store what in it? The ASCII code of the character, because you want it to have a character. Okay, so the ASCII code of the P. I don't remember it, but you can search it. The ASCII code of the P to be a number. Then the ASCII code of the L, small letter. Then the ASCII code of the E, small letter. Okay, and so on. Fill. The fill is a directive that fills a number of memory locations, yani fill 20, 40. The value, how many times? This will put a 20, 40 times. 20, 20, 20, 40 times in memory. Okay, this is the fill. If you want to initialize an array, whatever, I don't know what you can use it to.
دكتور
Yes.
فيل 20 هاي بكون محدد لي الادرس اللي بدي اسيف فيها.
قبليها احط origin 2000. So بتكون هذه 2000 وعد 2001 2002 لحد 40 more bytes.
دكتور بس سؤال صغير ممكن عن الكاركتر. هلا الكاركتر 8 بت صح؟
يس. ASCII كود. يس
الاسكي كود في منهم بالاسكي كود بعد ال 99 ممكن بيحجز 2 بايتس هون؟
لا ال 8 bit can take numbers from 0 to 255. Right?
كديسيمال.
decimal بالهكساديسيمال is 0 to FF, right?
FF. Okay.
ف 99 falls within this.
Yes.
Okay. Reserve memory byte, same as define storage or define storage byte. Reserve memory byte, we use this one, reserve memory byte. Buffer, يعني buffer. This is how we do it. Buffer, reserve memory byte, 100. This will book, and if this on the origin 1000, this will go to address 1000. Book 100 locations, 100 bytes, and just reserve them. Reserve them empty if you want to. And remember when we did the sum, we did the same. We booked 2 bytes for the sum to store our data later on, and it will give you a label here called buffer that you can access these locations through. Define storage word or reserved memory word, زي byte bus for words. So this will define storage word or reserved memory word. Will book how many bytes? How many bytes? 40 bytes يعني 20 words. So word هذا word 1 طيب, then word 2, and a word in C is an integer, right? Integer, unsigned integer, and 16-bit. Byte, the byte is an unsigned, and if you want to do the same in C, character. طيب, equate يعني wherever, for example here, Ali equates 1000. Okay, I can say origin Ali. This is exactly the same as origin 1000. Okay, the assembler, wherever it sees Ali, it will take it out and put 1000, replacing it. Equate. Locate. This is a directive that we use with labels like this case. Without the locate, if you have this code and here you want to branch to here and here is here, then branch let it be branch if not equal, branch if not equal, conditional branch. We'll get to conditional branches later. So it may branch or not, and it may continue. Then you can do a branch if not equal to here, and here is here. So this will confuse the assembler, okay? You either change the label names, so call this one here 1, here 1, and this one here 2, here 2. If you don't want to use these numbers, you can before say location, and it will send you back to the closest one to you. So here, look, backward tick mark. So you say branch if not equal to loop with this tick, it will send you back to here. This one will send you back to here, not to this one, the most recent one, lock. Macros. Macros are something close to directives. They are not assembly instructions. If I want to explain a macro, you give it you define it and say it's a macro, give it arguments and do something end macro. How is this helpful? Did you ever deal with macros?
زي مبدأ الفانكشنز دكتور.
لا okay, good discussion point. Let's discuss functions later. Okay, في subroutines عندنا احنا هون مش functions. Assume you want in your code, you always want to add 3 numbers, not 2 numbers. So you can say add accumulator A with memory location 1000. Add A. طيب, you want to add B with or add A, خليها add A with memory location 2000. So you have an instruction to add a register with a memory location. But what if you want to add the contents of memory location 1000 plus the contents of memory location 2000 and store the result in memory location 3000? Or you want to change, you do this all the time. You want something that adds the contents of 2 memory locations and stores the result in a third place. In another case, you want to add the contents of 3001 with 3002 and store the result in 1000. And you do this again and again and again. To do this, you need a few instructions. You need to add, let's say, to add the contents of memory location 1000 with 1001 and store the result at 1002. What do? We load accumulator A, right, with the contents of 1000. Then we add to A the contents of 1001. Then we store the result at 1002, right? Done. Like, what if I want to do this for the 3 memory locations at address 2000, 2001, and store the result at address 3000? I have to write these again, but with the new addresses, right? If this is something you always do, and you want to save time writing your code, again, highlight this, save time writing your code, you can do something like this. Say, add mem, مثلا add memory, أعطيها اسم, just like an instruction. I don't know what you want to call it. Add mem, and this is a macro. Call it a macro. See here. Give it a name. This is a name. Then it's a macro. Then you pass the arguments. Okay. You say name, add mem, macro, X, Y, Z. And I always want to add X plus Y and store the result in Z. So what you say, load accumulator A, X, add to A, Y, store A, accumulator A in Z, and M. Now to do the operations, so this is called a macro. طيب, خلاص, we're done with the macro. You can write it anywhere in your assembly file. What happened, man? طيب, you wrote it anywhere in your assembly file. Now you can just call it. You say add mem, and you pass these arguments in order. You say مثلا, if you had a label here at origin 1000, you had num1, define constant byte, وحطيت فيه whatever, num2, define constant byte, whatever, and num3 or some, whatever you want, form constant byte, 1 byte. You can just say here, add mem, num1, comma, num2, comma, sum. خلاص, it will replace num1, num2. This will go, the assembler will understand that I would need to replace this line of code with these 3 instructions. It will put load accumulator A, X is the first one with num1. Then add A, Y is the second argument, which is num2. Then store accumulator AZ is the third argument, sum. Store accumulator A at sum. So you don't have to write these again. You just say this. Okay, if I want to add 2000, 2001 and store 3000, you can say add mem 1000, 1001, 3000. Clear? Now, what the assembler does, it replaces this line of code you write with 3 instructions. So, بمعنى, if you have a program, this is your program, assembly. I wrote load, store, blah, 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 and then I called a macro here. Then I did want to add mem, اللي هي add mem هاي المacro, add mem macro. Then I add mem here. Then I did a few other instructions. I add mem here. What the assembler will do, the instructions will be there, the store will be there. Okay, the add mem will be converted into the 3 instructions you mentioned. Then the instructions, then this one will be replaced by the 3 instructions in the macro. Then you continue, then this one will be replaced with the 3 instructions in the macro that you specified here. So this does not save program memory, does not save program memory. And each of these is is replaced with 3 instructions. You did not save anything. So you have 3 instructions here, مثلا, reserving 10 bytes. They will also reserve 10 bytes in program memory here, 10 bytes every time you call it. So you're not saving program memory. What does it save you? It saves you effort to keep writing something over and over again. Clear, Omar?
تمام دكتور.
What you mentioned, the function, and here in assembly we call it a subroutine, is a different concept. You write a piece of code, and I covered this in class demo 2, and I'm gonna cover it again. If you have instruction 1, 2, 3, 4, okay, and your main program is here. Program is here at origin 4000, and this is in chapter 4. We're going to cover it. Your main program, you have load, accumulator A, store, accumulator A, blah 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 blah. Then you branch to subroutine, we call it, branch to subroutine my function, مثلا my function. Here you have a label, بكون تحتيه طبعا بس انا حاطه بجنبه عشان نشوف. my function at origin مثلا 5000 فيه instruction 1 2 3 4, and at the end you have a return from subroutine. And here you can continue, you can branch to subroutine again to my function, and then you can continue. What does this do? This is not like a macro. The subroutine is different than a macro. Your program counter points here. In the macro, the program counter points here, and it will continue going. And this instruction, number 1, is going to be found at this address, every time fetched and executed. While in the subroutine, you have your code written once. So it takes مثلا هذول 4 instructions, they only reserve 4 locations, or 4, يعني the size of these 4 instructions one time. Now when you branch, you did not replace this instruction with these 4. No, you made the program counter go here, but you saved the current program counter at something called stack, so you can go get back to it later. Then you send your program counter to here, execute these instructions, then you return back to here. You continue. You call it again. You call the function, or the branch to the subroutine. This will save the program counter in the stack. Okay. Make the program counter point to the first instruction in the subroutine, execute them. When you're done, you go to the stack, get back the value, put it in the program counter, and continue at the point where you were before calling a subroutine. So it's a different concept than a subroutine. We have a special topic in one of the chapters about subroutines. Okay, subroutines save memory space. Okay, and save writing, مثلا يعني effort writing things. Yeah, macros they can help you save time, but they don't save memory. Okay. Subroutines may take extra few cycles to execute because there is an overhead. Saving your current program counter, loading the program counter with the address where the subroutine is at, executing and then returning back. There are some overhead here, so may introduce some delays. That's not big deal. Okay, is the macro clear? Sum of 3. You give them 3 operands. You always do them. The assembler replaces the macro with the 3 instructions. Software development process. Okay. How much time do we have? 0. Okay, guys. And if you look at, I'm gonna finish. Don't worry. If you look at our syllabus, we have some topics about software development, model-based development, etc. And that's why we got the Arduino we're going to use. Software, as introduced in this book, you say, oh, you define your problem, you write the algorithm, then represent it in a flow chart, and then start programming, okay? The thing, this would work for undergraduates, but we're at a graduate level. I think we need to go deeper because in the real industry, the time spent here is, I don't want to be go to the extreme, but it may be more than 70% of the time developing a product, a software, embedded software product. 70% of the time may be spent here, and the value and the cost put on developing a software, embedded software, most of it is in this area before you start programming. Okay. So here they show you. Anybody not familiar with flowcharts? Anybody never dealt with flowcharts? Okay. So what's left here is they want to tell you plan for a program, design your program and present it in a flowchart, then write down the steps, then write the code. You shouldn't start writing code from the beginning. Okay. Next time I'm gonna try to go with you through an industry level from my personal experience in the industry, showing some tools, some different software development processes. One of them is the model-based approach that we're gonna use when we develop model-based embedded software and auto code generate for rapid prototyping and run it on our microcontroller and see all these benefits. Okay, this is the topic of next time. If you don't have any questions, you can leave. If you have questions, you can stay till after I finish my recording. Thank you very much and have a nice weekend. See you next Monday.